Look up at the night sky, and you'll see countless stars shining like distant diamonds, but hidden among them are some of the universe's most breathtaking and enigmatic masterpieces. Planetary nebulas, these glowing clouds of gas and dust, aren't just cosmic eye candy. They're the final, spectacular farewell of dying stars, painting the darkness with colors so vivid they defy imagination. And yet, for all their beauty, these celestial wonders are packed with mysteries that leave even the sharpest astronomers scratching their heads. Picture this: a star, much like our own sun, reaching the end of its life. Instead of fading quietly, it erupts in a dazzling display, shedding its outer layers in a fiery ballet that stretches light years across space. The result: a planetary nebula, a cosmic fingerprint with shapes so strange, so unpredictable, they've sparked debates for decades. Some twist into delicate spirals, others stretch like hourglasses or even form bizarre, asymmetrical knots. What forces sculpt these mesmerizing structures? Why do no two nebulas ever look the same? And what secrets do they hold about the fate of our own sun billions of years from now? That's exactly what we're diving into today. From ghostly rings that shouldn't exist to unexplained chemical fingerprints etched into their glowing cores, planetary nebulas are far more than just pretty space clouds. They're cosmic detectives, revealing clues about how stars live, die, and even recycle their remains into the building blocks of new worlds. So buckle up, because by the end of this journey, you'll never look at these celestial wonders the same way again. The universe is about to get a whole lot stranger. Take the Butterfly Nebula, a cosmic masterpiece that looks more like an artist's fantastical sketch than a natural phenomenon. Officially catalogued as NGC 6302, this nebula stretches its glowing wings across space with a symmetry so precise it's almost eerie. But here's the twist: those iconic wings shouldn't exist. Most planetary nebulas form slow, gentle expansions like bubbles blown by a dying star. Yet the butterfly's wings are sharp, dramatic, and stretch at impossible speeds, some parts rocketing outward at over 600,000 miles per hour. So what's bending the rules? Astronomers have two leading suspects. First, a hidden dance of stars. Many think the nebula's central star wasn't alone. It may have had a companion, a binary partner whose gravitational tug of war ripped the dying star's ejections into these exaggerated wings. Imagine two children spinning while holding a jump rope. The forces twist and stretch the rope into wild shapes. That might be exactly what happened here. The other culprit: magnetic fields stronger than anything in our solar system. Some observations suggest the dying star's magnetic field funneled its outbursts into those precise, jet-like wings, like squeezing toothpaste through a tube. But here's the real puzzle. The butterfly's wings aren't just fast, they're laced with complex chemical soups, including molecules that typically get destroyed in such violent environments. It's as if the nebula is defying physics, leaving behind clues that keep rewriting the rules. And the strangest part, even among bipolar nebulas, the butterfly is an outlier. Its structure is so extreme, so unlike anything else, that some researchers wonder if we're missing a crucial piece of the puzzle. Maybe it's not just binary stars or magnetism. Maybe something even more exotic is at play. One thing's certain: this celestial butterfly isn't just beautiful. It's a rebel, challenging everything we thought we knew about how stars say goodbye. Now shift your gaze to the Red Spider Nebula, a cosmic predator lurking in the constellation Sagittarius. Catalogued as NGC 6537, this nebula earned its arachnid nickname from the eerie, web-like filaments stretching through its glowing core. But what makes this celestial spider truly terrifying isn't its appearance, it's the unimaginable forces at work behind the scenes. The red spider's filaments aren't gently drifting clouds. They're being hurled into space by supersonic winds clocking in at over 300 kilometers per second. That's fast enough to race from Earth to the Moon in just 20 minutes, a velocity so extreme it defies traditional models of stellar death. When stars like our Sun reach their final act, they typically shed their outer layers in a slow, steady breeze. But the red spider, it's more like a cosmic hurricane, blasting material outward with enough force to shred its own remains into those haunting, thread-like structures. So what's powering these violent winds? The answer might lie in the nebula's tiny but ferocious core, a white dwarf star hotter than the surface of our Sun. Think of it like a pressure cooker gone rogue. As the dying star collapses into this scorching remnant, radiation floods outward, heating ejected gas until it's supercharged like steam escaping a valve. But here's where things get weird. Even with this heat, the winds here are twice as fast as most models predict. Some scientists suspect magnetic fields are acting like cosmic accelerators, whipping particles to these insane speeds. Others point to the star's rapid rotation, which might be slinging material outward like a spinning top flinging droplets. And the real kicker, these winds aren't just fast, they're chaotic. Observations reveal clumps and knots in the filaments, as if the nebula can't decide whether to tear itself apart or hold together. It's a stellar tantrum on a scale we can barely comprehend, forcing astronomers to rethink how stars lose mass in their death throes. Every new observation of the red spider adds another wrinkle, proving that when it comes to planetary nebulas, the universe loves throwing curveballs. One thing's certain, this isn't just a dying star. It's a cosmic laboratory, reshaping our understanding of the forces that govern stellar farewells, one supersonic filament at a time. Deep in the constellation Aquarius, a cosmic eye stares back at us with an eerie, unblinking gaze. The Helix Nebula, nicknamed the Eye of Sauron for its haunting resemblance to Tolkien's fictional menace, holds secrets far stranger than fiction. At first glance, this nebula appears as a simple, glowing ring, like a celestial smoke signal. But peer closer and you'll uncover something astonishing. Concentric dust rings rippling outward from its core, layer upon layer, like tree rings carved by a dying star. These ghostly rings tell a story of stellar violence long before the star's final act. Normally, when a star like our Sun nears death, it sheds its outer layers in one grand finale, creating the classic nebulous shapes we recognize. But the Helix didn't go quietly. Its rings suggest a series of explosive tantrums, repeated bursts of mass ejection over tens of thousands of years, each eruption freezing into dust and gas like snapshots of the star's slow unraveling. How does this happen? Imagine a pot of water boiling over again and again, leaving residue on the stove each time. The star, in its death throes, experienced violent pulsations, expanding and contracting as it burned through its fuel. With each pulse, it hurled material into space, creating these nested rings. But here's the twist, these ejections weren't perfectly even. Some rings are thicker, others fainter, hinting at unstable, sporadic outbursts rather than a steady, predictable process. Even more baffling is the spacing. These rings aren't random, they're evenly spaced, as if timed by some unseen stellar metronome. Some astronomers believe this points to a hidden companion, a smaller star or even a massive planet, whose gravitational nudges triggered these eruptions at regular intervals. Others argue it's the star's own internal heartbeat, a rhythmic instability in its core. But the real shocker, these rings are cold, far colder than the surrounding nebula. While the main structure glows from the white dwarf's intense radiation, the rings lurk in the shadows, untouched by the heat. It's like finding frost in the middle of a furnace, a contradiction that forces us to rethink how stars shed their skins. Each ring is a cosmic fossil, preserving the turbulence of a star's final millennia in breathtaking detail. And if that's not eerie enough, consider this: the Helix's rings stretch nearly 3 light-years across. That means the star's death rattle lasted longer than human civilization has existed. It's a humbling reminder that even in death, stars operate on timescales we can barely fathom, leaving behind clues that whisper across the ages. If the Helix Nebula is a cosmic eye staring across space, then the Boomerang Nebula is its ghostly breath frozen in time. Located 5,000 light-years away in the constellation Centaurus, this ethereal glow holds a record that's almost impossible to comprehend. It's the coldest natural place ever measured in the universe. At a bone-numbing -272 degrees Celsius, it's just 1 degree warmer than absolute zero, the theoretical temperature where all molecular motion stops. To put that in perspective, even the vast emptiness between galaxies isn't this cold. The Boomerang's chill is so extreme, it defies the laws of physics as we know them. So how does a nebula become colder than the void of space itself? The answer lies in its breakneck expansion. Unlike most planetary nebulas which shed their layers at a steady pace, the Boomerang is practically sprinting into oblivion. Its central star is ejecting material at a staggering 500,000 kilometers per hour, fast enough to cross the continental United States in less than 5 seconds. This explosive speed creates a cosmic refrigeration effect. As gas races outward, it expands and cools, much like the chill you feel when spraying compressed air from a can. But here, the scale is unimaginable. The nebula's outflow stretches over 2 light-years, creating a natural deep freeze larger than our entire solar system. The real mystery: this extreme cold shouldn't last. Normally, radiation from the central star or the cosmic microwave background, the faint afterglow of the Big Bang, would warm the nebula's edges. Yet the Boomerang remains frostier than anywhere else we've observed. Some scientists speculate its shape plays a role. The nebula's iconic bow tie structure might be funneling radiation away like a thermal shield. Others think the central star's unique properties, perhaps a rapid spin or magnetic field, are supercharging the cooling process, but the plot thickens. Recent Hubble observations revealed the nebula isn't perfectly symmetrical. One lobe is slightly warmer, hinting at an unseen companion star or a chaotic ejection event. Even the name Boomerang might be a misnomer. It actually resembles an hourglass more than a returning throw. Every new discovery peels back another layer, proving this nebula isn't just cold. It's a cosmic anomaly, rewriting our understanding of how stars engineer their final, frozen farewells. Among the countless planetary nebulas scattered through the cosmos, few are as hypnotic as the Twin Jet Nebula, officially known as M29. At first glance, it resembles a celestial hourglass with 2 shimmering lobes stretching into space like the wings of a cosmic butterfly. But what makes this nebula truly extraordinary isn't its shape, it's the frenetic dance happening at its heart. Most planetary nebulas form from a single dying star, but M29 defies the norm. Here, 2 stars orbit each other in a tight, gravitational embrace, locked in a partnership that shapes the entire nebula. The primary star, a red giant in its death throes, is shedding its outer layers in a dramatic farewell. But instead of expanding evenly in all directions, its ejected material gets caught in a gravitational tug-of-war, funneled into 2 opposing jets that carve out those iconic wings. The result, a nebula that looks less like a fading star and more like a cosmic scale spinning top, spraying twin streams of glowing gas into the void. The real mystery lies in the nature of this stellar duo. Some astronomers argue the companion isn't just a star. It could be a dense, compact object like a white dwarf or even a neutron star, its intense gravity sculpting the outflow into those precise, symmetrical jets. Others propose the second star might be surrounded by a thick disk, acting like a celestial stencil that shapes the escaping material. Imagine holding a garden hose underwater while twisting it. The spiraling water creates a specific pattern. That might be exactly what's happening here, but on a scale spanning trillions of miles. Adding to the intrigue, the twin jet's wings aren't static. Hubble observations reveal their swaying, almost like seaweed in a current. This suggests the central stars aren't just orbiting, they're wobbling, their dance floor tilting over time. Such precession, as astronomers call it, is rare in planetary nebulas, hinting at forces we're only beginning to understand. But the most tantalizing question remains, is this truly a binary system, or could the companion actually be a debris disk left behind by the dying star? Some models suggest the star's own rotation, amplified as it collapses, could create a disk massive enough to mimic a second star's gravitational influence. If true, it would rewrite our understanding of how single stars shape their final acts. One thing's certain, the Twin Jet Nebula isn't just a spectacle. It's a celestial laboratory offering a front-row seat to the complex physics of stellar farewells. Every twist of its wings, every ripple in its structure, whispers secrets about the turbulent relationships that govern life and death in the cosmos. Hidden among the countless nebulas dotting our galaxy, one stands out like a cosmic piece of blown glass, the etched hourglass, officially known as Mycian 18. Unlike the chaotic filaments of the red spider or the frosty expanse of the Boomerang, this nebula boasts a near-perfect hourglass shape, so precise it looks sculpted by an unseen hand. But the real magic here isn't just its symmetry, it's the invisible force field shaping it. Magnetism on a scale that bends our understanding of stellar depths. Most planetary nebulas owe their forms to violent stellar winds or the gravitational tugs of companion stars, but Mycian 18 dances to a different rhythm. At its core lies a dying star whose magnetic field is so powerful, it acts like an invisible loom, weaving ejected gas and dust into those flawless, narrowing curves. Picture a potter spinning clay, their hands guiding the material into a perfect vase, except here, the potter is magnetism and the clay is superheated plasma. What makes this nebula truly bizarre is how those magnetic fields interact with the star's dying breaths. As the star sheds its outer layers, the fields channel the outflow into two opposing cones, creating that iconic hourglass silhouette. It's a stellar-level version of squeezing a water balloon at both ends, forcing jets to shoot out the poles. But unlike the chaotic jets of the Twin Jet Nebula, these streams are eerily controlled, their edges razor-sharp. The real enigma, Mycian 18's structure defies expectations. Normally, magnetic fields weaken as material expands into space, but here they remain dominant even light years from the central star. Some researchers suspect the star's rapid rotation is dynamo charging these fields, like a turbocharged generator. Others point to the nebula's unusually dense central region, where trapped radiation might be amplifying the magnetic grip. And then there's the contrast. Compare Mycian 18 to, say, the Butterfly Nebula. Both are bipolar, yet their creation stories couldn't be more different. The butterfly's wings are carved by gravitational chaos and violent winds, while the etched hourglass is a masterpiece of magnetic precision. It's the difference between a wildfire and a laser cut. Yet for all its perfection, this nebula hides turbulence. Recent infrared observations reveal faint, jagged structures along its rim, hints that even magnetism's orderly reign has its limits. Perhaps the star experienced sporadic outbursts, or maybe an unseen companion stirred the pot. Whatever the case, Mycian 18 proves that even in death, stars can leave behind legacies of breathtaking order and mysteries that refuse to fit neatly into our models. One thing's clear, this isn't just another pretty cosmic cloud. It's a laboratory for the universe's most invisible forces, proving that sometimes the most powerful sculptors in space wield tools we can't even see. In the southern skies, nestled within the constellation Centaurus, lurks a celestial crustacean that defies all expectations, the Southern Crab Nebula, officially catalogued as He2104. At first glance, this cosmic oddity resembles a lobster's claw. Its pincers formed by two nested hourglasses of glowing gas, one cradled inside the other like a Russian doll carved from starlight. But this bizarre structure isn't just a quirk of perspective. It's the handiwork of one of the universe's most volatile relationships, a symbiotic star system where two stars, locked in a deadly tango, are tearing each other apart in spectacular fashion. The Southern Crab's central duo is a textbook case of cosmic codependency gone wrong. A red giant, bloated and unstable, orbits a white dwarf, the dense, fiery remnant of a long-dead star. As the red giant sheds its outer layers, the white dwarf greedily siphons off this material, forming a swirling disk around itself. But this cosmic theft comes at a price. Periodically, the disk becomes unstable, triggering thermonuclear explosions on the white dwarf's surface. These eruptions blast material outward in opposite directions, carving the nebula's iconic hourglass shapes. Here's where it gets truly strange. Most hourglass nebulas form a single structure, but the Southern Crab boasts two, one smaller and younger, nestled inside the larger, older shell. This suggests the system has erupted multiple times, with each outburst sculpting a new layer. It's as if the stars are trapped in an endless cycle of creation and destruction, like a phoenix that keeps rising from its own ashes only to burn again. The real puzzle lies in the precision of these eruptions. The nested hourglasses aren't just stacked, they're eerily aligned, their axes perfectly parallel across light years of space. This level of symmetry implies an unseen guiding force, perhaps the white dwarf's spin or its magnetic field, orchestrating each explosion with machine-like precision. Some astronomers even speculate the larger hourglass might be acting like a cosmic funnel, shaping the newer outbursts into its mold. But the Southern Crab isn't just a pretty illusion. Its lobes are laced with turbulent knots and braided filaments, evidence of violent collisions between old and new ejecta. These chaotic details hint at a system teetering on the edge of stability, where even the slightest gravitational nudge could trigger another cataclysm. And then there's the lobster claw illusion itself. Those iconic pincers aren't solid structures but glowing arcs of shock-heated gas, where the white dwarf's outbursts slam into slower-moving material ejected earlier. It's a celestial collision frozen in time, a snapshot of stellar violence so vivid it feels almost tactile. What makes E2104 truly exceptional, though, is its rarity. Symbiotic systems like this are cosmic unicorns. Fewer than a dozen are known to produce nebulas, and none display this nested hourglass phenomenon. It's a reminder that even in the vast, law-abiding universe, there's always room for a rebel. A pair of stars dancing on the edge of destruction, writing their own rules in luminous gas. Glowing in the constellation Hydra like a cosmic lighthouse, the ghost of Jupiter Nebula, officially NGC 3242, lives up to its eerie nickname. But this celestial spectre isn't just haunting the night sky with its ghostly glow. It's flickering, its brightness fluctuating in ways that defy easy explanation. While most planetary nebulas fade predictably over millennia, NGC 3242 dances to a far more erratic rhythm, dimming and brightening on timescales as short as decades. It's as if the nebula's central star is flipping a cosmic light switch, leaving astronomers scrambling to decode its cryptic signals. The heart of this mystery lies in the nebula's white dwarf, a stellar corpse so active it practically crackles with energy. Typical white dwarfs cool quietly like fading embers, but this one behaves more like a restless spirit, periodically surging in brightness. Some researchers attribute these spikes to unstable nuclear reactions still smoldering on its surface, while others suspect violent stellar winds pushing shockwaves through the nebula's delicate structure. Imagine blowing on a dandelion repeatedly. Each breath reshapes the seeds in unpredictable ways. That's the kind of chaos unfolding here, but on a scale spanning trillions of miles. What makes these fluctuations even stranger is their visibility to amateur astronomers. Unlike distant galactic phenomena requiring massive telescopes, NGC 3242's changes are detectable with backyard equipment. Citizen scientists worldwide have become crucial detectives in this cosmic whodunit, documenting its dimming through decades of patient observation. Their data reveals a startling trend. The nebula's outer edges are fading faster than its core, as if something, perhaps an invisible companion star or an uneven magnetic field, is tipping the scales of its decay. The real puzzle: these brightness shifts don't align with any known stellar death models. Most white dwarfs shed their energy in slow, steady declines, but the ghost of Jupiter's flickers suggests turbulence beneath the surface. Some theories propose submerged convection currents like boiling water trapped beneath a lid that occasionally burst through, while others point to accretion disks of debris left over from the star's violent past. Whatever the cause, one thing's clear: this nebula refuses to fade quietly. Its tantrums are rewriting the textbook on how stars transition from luminous giants to cold, dark remnants. And there's a deeper lesson here. The ghost of Jupiter reminds us that even in death, stars aren't monolithic. They sputter, flare, and resist uniformity, leaving behind fingerprints as unique as snowflakes. For astronomers, that unpredictability is a gift, a chance to study the messy, unfinished business of stellar evolution in real time. Every flicker is a clue, every dimming a whispered secret about the forces that govern a star's final act. Most stars take millennia to sculpt their final masterpieces, but the Stingray Nebula Hen 31357 is rewriting the rules in real time. Discovered in the 1980s, this celestial upstart wasn't just young by cosmic standards. It was practically newborn, flashing into existence so recently that astronomers have watched it evolve within a single human lifetime. While most planetary nebulas fade over tens of thousands of years, the Stingray has transformed dramatically since its discovery, offering an unprecedented front-row seat to the chaotic birth of a nebula. What makes this object so extraordinary is its speed. When first observed, the Stingray was little more than a faint, blobby haze around a hot central star. But by the 1990s, it had sprouted delicate wings of ionized gas, earning its aquatic nickname. Then, in just 2 decades, Hubble images revealed something astonishing. The nebula's brightness dropped by a factor of 1,000, and its delicate structures began fading like a vanishing act. No other planetary nebula has ever been caught changing this fast. It's as if we're watching a time lapse of stellar death compressed into decades instead of eons. The culprit: a central star behaving like a cosmic drama queen. Most stars transitioning into white dwarfs do so gradually, but the Stingray's progenitor is cooling at breakneck speed. As its temperature plummeted from 60,000 to under 30,000 degrees Celsius in mere decades, the radiation needed to excite the nebula's gas vanished almost overnight. Imagine turning down a stove burner and watching the steam above it dissolve in real time. That's the level of change astronomers are witnessing here. Yet the Stingray's youth reveals more than just stellar temper tantrums. Its rapid transformations suggest that the earliest phases of planetary nebula formation might be far more volatile than we thought. Traditional models assumed these structures emerged slowly, like a flower blooming. But the Stingray's outbursts hint at fits and starts violent ejections followed by eerie quiet, as if the star can't decide how to die. Some researchers now think this stop-and-start process could be the norm, with older nebulas simply smoothing out over time. And then there's the nebula's chemical fingerprint. Spectroscopic studies show bizarrely high levels of neon, an element typically forged deep in a star's core and only uncovered during its final throes. This suggests the Stingray's progenitor might have ripped itself apart unevenly, scattering pockets of pristine core material into its ejector like ingredients spilled from a cosmic pantry. The implications are profound. If the Stingray represents planetary nebulas in their infancy, then many of the serene, symmetrical structures we admire, like the etched hourglass or the helix, might have begun as turbulent, rapidly changing chaos. It's a humbling reminder that even in the vast, slow-moving cosmos, some of the most spectacular transformations can happen in the blink of a celestial eye. The Cat's Eye Nebula, known to astronomers as NGC 6543, has long captivated skywatchers with its hypnotic, onion-like layers, but hidden within those shimmering rings lies an explosive secret. When NASA Chandra X-ray Observatory turned its gaze toward this cosmic gem, it detected something utterly unexpected: searing X-rays blazing from its heart. This wasn't just a gentle glow, it was the signature of violent shock waves ripping through space at millions of miles per hour, a phenomenon rarely seen in planetary nebulas. The discovery turned decades of assumptions upside down, revealing that even the most delicate-looking cosmic structures can harbor unimaginable turbulence. So what's generating these high-energy X-rays? The answer lies in a celestial demolition derby happening at the nebula's core. As the dying star at the center of the Cat's Eye shed its outer layers, it didn't release them in a steady breeze. It hurled them outward in furious gusts, like a cosmic engine revving unpredictably. These fast winds, traveling at over 6 million kilometers per hour, later crashed into slower-moving material ejected earlier, creating titanic shock waves. Picture two highways merging at wildly different speeds. When the fast-moving traffic slams into the slower lanes, the collision releases tremendous energy. In the Cat's Eye's case, that energy manifests as X-rays, superheating gas to temperatures hotter than the surface of the Sun. But here's the twist: most planetary nebulas don't emit significant X-rays. Their expanding shells usually dissipate energy more gently, like a balloon deflating. The Cat's Eye's intense X-ray output suggests its central star experienced violent, spasmodic outbursts rather than a smooth decline. Some researchers speculate a binary companion might be stirring the pot, its gravitational nudges triggering erratic ejections. Others propose the star's own magnetic field went haywire, channeling material into chaotic jets that collided at odd angles. Even more puzzling is the X-rays' distribution. Instead of a uniform glow, Chandra found them concentrated in specific regions like hotspots where the shock waves are most ferocious. These zones align eerily with the nebula's intricate loops and knots, hinting that the same forces sculpting its famous rings are also powering these high-energy tantrums. It's a reminder that beauty and violence often go hand in hand in the cosmos. The Cat's Eye's X-ray surprise does more than dazzle astronomers. It rewrites the playbook on how stars die. If shock waves like these are common, even in nebulas as seemingly serene as this one, then our understanding of stellar winds and their aftermath might need a radical update. Every flicker of X-ray light from this cosmic feline is a clue whispering secrets about the turbulent final chapters of a star's life. Among the chaotic swirls and asymmetric outbursts of most planetary nebulas, Cronberger 61 stands out like a cosmic anomaly, a perfect, glowing sphere so precise it earned the nickname the Soccer Ball Nebula. This celestial rarity, located 13,000 light-years away in the constellation Cygnus, defies expectations with its near-flawless symmetry. While most dying stars produce lopsided or bipolar ejections, Cronberger 61's shell expands almost uniformly in all directions, as if the star took its last breath with perfect spherical calm. What could explain such mathematical perfection? Astronomers are torn between two compelling theories. The first suggests Cronberger 61's progenitor star was exceptionally isolated, free from the gravitational tugs of binary companions or dense interstellar clouds that typically distort nebula shapes. Like a balloon inflating in empty space, its ejected layers expanded undisturbed, creating this rare spherical symmetry. But the second theory is far more intriguing. This nebula might be the fingerprint of a unique type of stellar death. Some researchers propose the central star belonged to a rare class known as hydrogen-deficient stars, which shed their outer layers in unusually smooth spherical outbursts. These stars burn through their fuel in unconventional ways, leaving behind chemical signatures that could explain the soccer ball's pristine form. Spectroscopic studies reveal oddities in its composition, unusually high levels of helium and carbon, hinting at exotic nuclear processes in its final moments. Yet even these explanations don't fully account for the nebula's crisp edges. Most spherical nebulas show at least some irregularities, but Cronberger 61's shell is remarkably sharp, almost as if sculpted by an unseen force. Some theorists speculate its central star's magnetic field acted like an invisible mold, constraining the outflow with unprecedented precision. Others wonder if we're witnessing a statistical fluke, a fleeting moment in the nebula's evolution where turbulence briefly settled into perfect order. Adding to the mystery, the soccer ball's glow isn't uniform. Delicate filaments lace its interior, suggesting hidden currents or shock waves rippling beneath the surface. These subtle imperfections reveal that even in this cosmic ideal of symmetry, there's invisible chaos at work. Perhaps the most humbling lesson here is that no stellar death is ever truly simple. Even the most symmetrical nebulas guard secrets that defy our neatest theories. One thing's certain, Cronberger 61 isn't just a pretty oddity. It's a challenge, forcing us to reconsider how stars die when left to their own devices. In a universe that favors turbulence and asymmetry, this celestial soccer ball is a quiet rebel, proof that sometimes nature's most breathtaking artistry emerges from the simplest rules. Somewhere in the constellation Sagittarius, a cosmic jewel heist unfolds. The Helix Nebula, catalogued as PNG 054.2-03.4, dangles in space like a trillion-mile-wide pendant. But those glittering diamonds embedded in its glowing ring aren't gems at all. They're the shattered remains of a stellar crime scene, forensic evidence of one star cannibalizing another. This twisted tale begins with two stars locked in a close orbit, a bloated giant and its smaller companion. As the giant star expanded in its death throes, it didn't just gently shed its outer layers, it engulfed its partner whole, swallowing it like a cosmic predator. Yet this act of stellar devouring backfired spectacularly. The swallowed star, unwilling to vanish quietly, began spiraling violently through its captor's atmosphere, churning up gas like a blender until the larger star could no longer hold itself together. The result, a catastrophic ejection that hurled material outward in dense, clumpy waves, those very diamonds we see today, each one a frozen ripple in this gravitational massacre. What makes these knots so extraordinary is their composition. Hubble's spectroscopic analysis revealed they're packed with oxygen, nitrogen, and neon elements typically forged deep in stellar cores. Their presence here suggests the violent encounter dredged up material from both stars' innermost layers, scattering it like cosmic shrapnel. Even more telling are the knots' arrangement. They're strung along the nebula's ring with eerie regularity, spaced roughly 150 billion miles apart. This uniform pattern points to the orbital dynamics of the doomed binary pair, their final dance imprinted on the nebula's structure like grooves in a vinyl record. But the real smoking gun lies at the nebula's heart. Modern observations reveal not one, but two stellar remnants, the white dwarf left behind by the giant star, and the surviving core of its companion, now stripped bare by the ordeal. They still orbit one another feverishly, completing a revolution every 1.2 days, a grim testament to the event that birthed this celestial necklace. The Helix Nebula does more than dazzle, it documents a stellar homicide in progress, offering astronomers a blueprint for how binary systems can transform into some of the universe's most bizarre structures. Those glittering knots aren't just debris, they're a cosmic autopsy report spelling out in gaseous ink how stars can rewrite each other's fates. At first glance, the blue snowball nebula NC 7662 lives up to its poetic name, appearing as a flawless, icy blue orb suspended in the cosmos. But recent observations tore that serene illusion to shreds. Hidden within this seemingly perfect sphere are ghostly, high-speed jets shooting from its poles like invisible fountains, structures so faint they eluded detection for centuries. These aren't just ornamental details, they're the fingerprints of a dying star's violent tantrum, rewriting the story of what we thought was one of the galaxy's most symmetrical nebulas. The jets came to light thanks to advanced narrowband imaging, a technique that isolates specific wavelengths of light emitted by ionized gas. What appeared as a smooth, featureless ball in early telescopes now reveals twin outflows stretching over half a light year, their paths slightly misaligned as if the star shuddered during ejection. Their presence flips the script on the blue snowball's formation. Instead of a calm, spherical expansion, we're seeing evidence of a star that fought its own demise, channeling its death throes into focused, bipolar eruptions before the slower-moving outer shell smoothed everything over like cosmic makeup. But why do these jets matter? For starters, they challenge the snowball nickname entirely. Most spherical nebulas form when stars shed their outer layers evenly, like a balloon deflating. The blue snowball's hidden jets prove its symmetry is just a facade, a celestial magic trick where chaos lurks beneath the surface. The misaligned jets suggest the central star might have wobbled as it ejected material, possibly due to an unseen companion's gravitational nudge or an unstable rotation. Imagine spinning a garden sprinkler while it's turned on. The jet's crooked paths could be the stellar equivalent of that erratic motion. Even more intriguing is their composition. Spectroscopy reveals these jets are richer in nitrogen and helium than the surrounding shell, hinting they originated from deeper within the star, like a puncture wound spewing core material into space. That means they're not late-stage afterthoughts. They're direct products of the star's death spasms, carrying pristine samples of its internal chemistry. The bigger picture, the blue snowball isn't the outlier we thought. Its hidden jets suggest even the most symmetrical nebulas might harbor bipolar tendencies, smoothing over their turbulent origins over millennia. It's a cosmic reminder that in the universe, first impressions are often just the tip of the iceberg. What looks like a serene celestial snowball might actually be the aftermath of a stellar storm. If the Southern Crab Nebula resembles a carefully constructed piece of celestial jewelry, then OH2 1.8 plus 4.2, better known as the Calabash Nebula, is its polar opposite, a cosmic splatter painting flung across space. Dubbed the Rotten Pumpkin Nebula for its grotesque, asymmetrical shape, this chaotic cloud of gas and dust looks less like a stellar farewell and more like a star violently vomiting its guts into the void. But beneath its unappetizing appearance lies something far more menacing, a stellar time bomb ticking toward one of the universe's most cataclysmic events, a supernova. The Calabash's tortured structure tells the story of a star in its death throes, but not the gentle, poetic kind. Here, a massive dying star, many times heavier than our Sun, is hemorrhaging material at speeds exceeding 700,000 kilometers per hour, ejecting globs of gas in every direction like a broken fire hose. Unlike the precise rings of the helix or the symmetrical wings of the etched hourglass, this nebula's ejecta are twisted, knotted, and shockingly uneven. Hubble images reveal tendrils of molecular gas writhing outward, some colliding to form dense clumps while others stretch into wispy filaments. It's as if the star couldn't decide how to die, so it tried every possible method at once. What makes the Calabash truly unique is its central engine, a rare, born-again giant. Most stars pass through their red giant phase once before collapsing into a white dwarf, but this one defied expectations. After initially shedding its outer layers, it reignited nuclear fusion in a desperate last stand, ballooning back into a red giant before exploding outward a second time. This cosmic encore created overlapping waves of ejecta, each collision generating shock fronts that heat gas to millions of degrees. The result, a nebula that glows not just from starlight, but from the raw violence of its own expansion. And the chaos isn't over. The Calabash's central star is destined for one of the most spectacular deaths imaginable. Unlike typical planetary nebula progenitors, which fade into white dwarfs, this star's core is so massive it will continue collapsing until poof, it detonates as a type Roman II supernova. When that happens, the nebula's already turbulent structure will be blasted apart, scattering enriched material across interstellar space. Until then, the calabash serves as a grisly preview of cosmic recycling in action, a stellar corpse preparing to fertilize the galaxy with the very elements that might one day form new stars, planets, or even life. But the real lesson here, the universe doesn't always play by the rules. While most dying stars bow out with grace, some, like the calabash's progenitor, go kicking and screaming, leaving behind not a serene monument, but a messy, magnificent tantrum frozen in time. The Medusa Nebula, officially catalogued as Able 21, haunts the constellation Gemini like a cosmic ghost, its faint tendrils barely visible even through powerful telescopes. For decades, this celestial spectre slipped through the cracks of astronomical surveys, dismissed as a mere smudge or photographic artifact. Its ethereal glow, 1,000 times dimmer than the famous Orion Nebula, made it one of the last major planetary nebulas to be recognized for what it truly is, the final, fading breath of a star that died long before humans walked the Earth. What makes the Medusa so elusive isn't just its faintness, it's the speed of its vanishing act. While nebulas like the Helix or Cat's Eye glow brightly for tens of thousands of years, the Medusa's delicate filaments are dissipating at an alarming rate. The reason lies in its unique anatomy. Unlike younger, denser nebulas, the Medusa's gas has expanded so far, stretching over 4 light-years, that its particles rarely collide, leaving them unable to efficiently absorb and re-emit the central star's dwindling light. Imagine a campfire smoke dissipating on a windy night. The Medusa's structure is similarly fragile, its glow fading as it thins into the void. But there's another twist. The Medusa's central star has cooled into an unusually dim white dwarf, robbing the nebula of the intense ultraviolet radiation needed to keep its gases ionized and luminous. Most planetary nebulas shine because their hot central stars act like cosmic blacklights, exciting the surrounding material. The Medusa's star, however, has transitioned into a quiet, aging remnant, leaving its nebula to fade like a forgotten neon sign. Yet this faintness reveals something profound about stellar life cycles. The Medusa isn't an anomaly, it's a preview. Every planetary nebula will eventually follow this same path, their vibrant colors dimming as they disperse into the interstellar medium. What makes the Medusa special is its position on this timeline. We're catching it in its twilight, a phase most nebulas pass through too quickly for us to observe. Its fragility offers a rare glimpse into the universe's quiet recycling program, where even the most dazzling structures dissolve, their atoms destined to be reborn in new stars, planets, or perhaps even life. So while the Medusa may lack the flash of its brighter cousins, its whisper-thin glow carries a message just as dramatic, a reminder that in the cosmos, even death has stages, and the most fleeting moments can be the most revealing. The Saturn Nebula NGC 7009 glows like a cosmic doppelganger of its namesake planet, complete with eerie, ring-like extensions stretching from its poles. But these aren't icy chunks orbiting a gas giant. They're searing hot strands of stellar material, twisted into perfect loops by forces we're only beginning to unravel. What's sculpting these celestial hoops? The leading theory points to an unseen accomplice, a companion star whose gravitational pull is shaping the nebula's final act into a masterpiece of symmetry. Picture Saturn's iconic rings, but instead of frozen debris, imagine superheated gas channeled into twin jets, then bent backward by stellar winds into those iconic arcs. This isn't just a pretty analogy, it's a clue to the violent physics at play. While Saturn's rings formed from shattered moons or ancient cosmic collisions, the Saturn Nebula's rings are starlight itself, ionized and sculpted by a hidden dance of gravity and radiation. Hubble's sharp eye revealed faint structures within these loops, braided filaments and knots that suggest the central star's outbursts weren't steady, but came in fits and starts like a sputtering hose suddenly jammed into a spinning top. The real enigma lies in the precision of these polar rings. They're not just vaguely symmetrical, they're mathematically aligned as if guided by an invisible hand. That's where the binary companion theory gains traction. Many astronomers suspect a second star orbits the nebula's white dwarf, its gravity funneling ejected material into those crisp equatorial rings. Think of it like a stellar potter's wheel. As the dying star spews gas, the companion's pull shapes it into orderly hoops rather than a chaotic cloud. But here's where the cosmic plot thickens. Unlike Saturn's icy rings, which are passively stable, the Saturn Nebula's rings are dynamic crime scenes. Spectroscopic studies reveal they're laced with shock waves, evidence of supersonic collisions between fast-moving stellar winds and slower-moving ejecta. It's as if the star's death throes were caught in a gravitational tug-of-war, leaving behind these luminous scars, and then there's the chemical fingerprint. The rings glow unusually bright in oxygen-rich emissions, suggesting the central star unearthed deep, primordial layers of its core during its death spasms. This isn't just a farewell, it's a stellar autopsy revealing ingredients normally hidden beneath a star's surface. The Saturn Nebula does more than mimic a planet, it challenges our assumptions about how stars die. Those elegant rings aren't just decoration, they're a cosmic breadcrumb trail leading us toward a deeper truth that even in death, stars rarely act alone. Whether it's a hidden companion, a magnetic field, or some undiscovered force, the universe loves a good partner act, and in this case, the collaboration paints one of the sky's most hauntingly beautiful farewells. The Little Dumbbell Nebula, officially catalogued as M76, might look like a cosmic afterthought compared to its flashier cousins, but peer closer, and you'll uncover a celestial oddity hiding in plain sight. Nestled in the constellation Perseus, this nebula sports two unmistakably mismatched lobes, one blazing with intense fluorescence, the other dim and ghostly, like a flashlight with dying batteries. This lopsided glow isn't just a trick of perspective, it's evidence of a dying star's uneven demise, and astronomers are locked in a heated debate over what caused it. One camp argues the star itself is to blame. As it shed its outer layers, they propose, it did so in fits and starts, with one hemisphere erupting more violently than the other. Imagine a soda bottle shaken and uncapped haphazardly foam bursts out one side while the other barely trickles. If the star's rotation or internal convection was lopsided, its ejections could have followed suit, leaving one lobe denser and brighter. Spectroscopic studies lend credence to this idea, revealing chemical asymmetries patches where elements like nitrogen and oxygen are oddly concentrated, as if the star's guts were spilled unevenly. But others point to forces beyond the star. The dimmer lobe might have plowed into an invisible wall of interstellar gas, its material slowed and scattered like a wave hitting a reef. Radio observations hint at faint wisps of external material surrounding M76, though whether they're dense enough to reshape the nebula remains contentious. There's also the wild card of magnetic fields. If the dying star's magnetic poles were wildly unbalanced, they could have funneled material preferentially in one direction, like a sprinkler with a clogged nozzle. The most tantalizing clue, the nebula's central star is missing. Most planetary nebulas proudly display their white dwarf progenitors, but M76's heart is eerily dark, leading some to speculate the star might have had a companion that disrupted its death throes. Binary interactions could explain the asymmetry. Think of two dancers spinning while one flings ribbons erratically. Yet without direct evidence, this remains a cosmic whodunit. What makes the Little Dumbbell truly remarkable is its defiance of expectations. In a universe that favors symmetry, this lopsided relic reminds us that stellar deaths are as unpredictable as they are beautiful. Whether it's a tale of internal chaos or external interference, one thing's clear: this nebula's twin personalities are a masterclass in cosmic individuality. Swirling in the constellation Gemini like a cosmic portrait frozen in time, the Eskimo Nebula NGC 2392 stares back at us with an uncanny resemblance to a face bundled in a fur-lined parka. Those delicate, rippling filaments encircling its central star aren't just whimsical features. They're the scars of a stellar battle between radiation and gravity, a showdown so violent it left the nebula's structure permanently ruffled. Zoom in and you'll find the fur isn't soft or uniform. It's a chaotic web of dense knots and tendrils, each one a monument to the dying star's turbulent final act. As the star shed its outer layers, its intense ultraviolet radiation blasted outward, heating the ejected gas until it glowed. But here's where things get messy. Instead of expanding smoothly, that radiation encountered pockets of cooler, denser material remnants of earlier, slower ejections, and slammed into them like a hurricane hitting a seawall. The collisions sculpted the gas into those iconic filaments, freezing the shockwaves in place like cosmic brushstrokes. What makes these structures even stranger is their layered history. The nebula's inner face is relatively smooth, a bubble of hot gas inflated by the star's fast winds. But the outer hood is all texture, its complexity betraying multiple episodes of mass loss. Imagine a snowball rolling downhill, picking up dirt and twigs along the way. The Eskimo's fur is the stellar equivalent, built up from material ejected at different speeds and times. But the real mystery lies in the filament's resilience. Despite the central star's scorching radiation, hotter than 100,000 degrees Celsius, these structures persist, defying expectations. Some researchers think magnetic fields are acting like cosmic glue, holding the knots together against the onslaught. Others point to chemistry, suggesting molecules like hydrogen and carbon monoxide form microscopic shields, protecting the densest clumps from evaporation. And then there's the question of symmetry. Unlike the Butterfly Nebula's dramatic wings or the Saturn Nebula's perfect rings, the Eskimo's fur is asymmetrical, thicker on one side, as if the star coughed more violently in one direction. This lopsidedness hints at unseen forces, perhaps a companion star's gravitational tug, or an uneven magnetic field that channeled material unevenly. One thing's certain: the Eskimo Nebula isn't just a pretty face. Its textured hood is a cosmic diary, recording every gasp and sputter of its progenitor star's death throes. And as we decode its turbulent history, we're reminded that even in the vast, unforgiving vacuum of space, the slightest imbalance can leave a mark lasting millennia. The Aunt Nebula Menzel 3 doesn't just bear a passing resemblance to its insect namesake. It's a near-perfect cosmic replica, complete with a segmented body and delicate, curling antennae stretching into space. At first glance, this eerie mimicry feels almost intentional, as if the universe itself decided to sculpt a celestial tribute to Earth's tiny inhabitants. But looks can be deceiving. What appears to be artistic coincidence is actually a violent physics experiment playing out on a scale spanning trillions of miles, and astronomers are locked in a fierce debate over the forces behind this uncanny shape. One camp argues the ant-like silhouette is pure chance, a fleeting alignment of gas and perspective that our pattern-seeking brains can't help but recognize. After all, nebulae eject material in all directions, and sometimes those chaotic outflows momentarily resemble familiar forms when viewed from just the right angle. But the opposing view holds something far more intriguing. That Menzel 3's shape isn't accidental at all, but the inevitable result of hidden forces sculpting its outflow with terrifying precision. The evidence pinpoints symmetry. Unlike the Butterfly Nebula's dramatic wings or the red spider's tangled filaments, the ant's body and antennae are eerily balanced, suggesting an invisible guiding hand. High-resolution Hubble images reveal those iconic antennae aren't random wisps, they're tightly wound spirals, their curves mathematically consistent with material being flung outward by a spinning, wobbling central star. Picture a figure skater spinning with outstretched arms, then suddenly tucking them in. As the star's rotation speeds up, its ejected material gets whipped into these precise corkscrew patterns, etching the illusion of antennae into the cosmos. But the real mystery lies in the nebula's waist, a pinched, hourglass-like middle that gives the ant its segmented appearance. This narrowing defies expectations, as most dying stars shed their layers in all directions equally. The leading theory, a binary companion. Just as the southern crab's nested hourglasses hint at a gravitational dance, Menzel 3's pinched waist might trace back to an unseen partner star, its gravity funneling material into twin outflows. Some models even suggest the companion could be a white dwarf, its intense radiation carving those antennae like jets, like a cosmic blowtorch. Yet the Ant Nebula isn't just a static sculpture. Spectroscopic studies show its gas is laced with shock waves, proof that those elegant curves are actually supersonic collisions frozen in time. The antennae glow brighter in certain wavelengths, revealing pockets where fast-moving stellar winds slam into slower ejecta, heating them to millions of degrees. It's a reminder that this delicate illusion is forged in chaos. A star's death throws so violent they momentarily mirror life itself. Whether coincidence or physics, one thing's certain: the Ant Nebula challenges our instinct to see order in randomness. Its mimicry forces us to confront a deeper question: are these shapes truly rare, or are we only just beginning to recognize the universe's hidden patterns? For now, Menzel 3 remains both a masterpiece and a riddle, its cosmic performance blurring the line between accident and design. Gazing out from the constellation Ursa Major, the Owl Nebula, officially known as Messier 97, earned its name not just from its round shape, but from two haunting, dark voids that pierce its glowing shell like hollow, unblinking eyes. These eerie gaps aren't random flaws, they're cosmic cavities carved by the final, gasping breaths of a dying star, revealing secrets about its turbulent demise. At first glance, the owl's eyes seem simple, just patches where the nebula's fluorescent gas thins out. But peer deeper, and these voids transform into a stellar autopsy report. The central star, now a cooling white dwarf, didn't eject its outer layers evenly. Instead, it coughed them outward in fits and starts, leaving behind pockets of lower density gas where radiation and stellar winds punched through like cosmic blowtorches. Imagine blowing smoke rings, but instead of smooth hoops, the gaps warp and twist as turbulent forces disrupt the flow. That's the kind of chaos etched into the owl's gaze. What makes these cavities particularly fascinating is their connection to the star's evolutionary stage. Most planetary nebulas glow brightly because their central stars flood them with ultraviolet light, exciting the surrounding gas. But the owl's star has cooled dramatically, its radiation waning like a dimming light bulb. Without that intense energy, the nebula's outer regions have begun to fade, leaving those eyes as stark reminders of where the star's influence faltered first. It's as if the nebula is literally losing its luminosity, its hollow gaze a testament to the star's quiet surrender. Yet there's a twist. Recent spectral analysis reveals those dark patches aren't entirely empty. They're threaded with faint filaments of molecular hydrogen leftovers from the star's earlier, more violent ejections. These ghostly strands suggest the cavities formed where fast-moving stellar winds collided with slower debris, carving out bubbles that later thinned into voids. It's a cosmic version of erosion, where gusts of charged particles act like interstellar sandblasters. The owl's structure holds another clue. Its overall shape, a near-perfect sphere, is surprisingly rare among planetary nebulas. Most, like the butterfly or the ant, display dramatic bipolar forms, but the owl's symmetry implies its progenitor star shed its layers relatively calmly, without the gravitational interference of a binary companion or a disruptive magnetic field. That simplicity makes it a cosmic control subject, a baseline for understanding how solitary stars die when left to their own devices. But don't let that tranquility fool you. Even in its serenity, the Owl Nebula whispers of violence. Those hollow eyes, they're not passive gaps. Their edges shimmer with shock fronts, invisible boundaries where stellar winds still push against the nebula's outer shell, slowly reshaping it. Over millennia, those forces will erode the owl's features entirely, dispersing its glow into the void. For now, though, its eerie gaze lingers, a fleeting monument to a star's final, gasping act, and a reminder that even in death, the universe leaves behind puzzles etched in light and shadow. The lemon-sliced nebula IC3568 gleams like a cosmic citrus wedge floating in the blackness of space. Its nearly perfect spherical shell so pristine it could pass for a child's drawing of a star's farewell. Yet nestled within this simplicity lies a puzzle, a core of chaotic turbulence belying the nebula's serene exterior. While most planetary nebulas flaunt intricate loops, jets, or asymmetrical outbursts, the lemon slice defies the trend, presenting astronomers with a paradox, a calm exterior masking a stormy heart. At first glance, IC3568's symmetry suggests a quiet death. Unlike the butterfly's frenzied wings or the southern crab's nested hourglasses, this nebula's gas appears to have expanded evenly in all directions, like a bubble blown into the void. But zoom in on its core and the illusion shatters. High-resolution images reveal a white dwarf star crackling with activity, surrounded by a churning maelstrom of gas knots and shock waves. This isn't the gentle fade out of a solitary star, it's the signature of hidden violence. So why the disconnect? One theory points to isolation. The lemon slice might be the cosmic equivalent of a hermit's final breath, a star so distant from gravitational influences like binary companions or dense interstellar clouds that its ejecta expanded undisturbed, smoothing into that flawless sphere. Yet its turbulent core hints this star didn't go quietly. Spectroscopic studies detect bizarrely high levels of ionized helium near the white dwarf, suggesting temperatures hot enough to strip atoms bare, a clue that the star's death throes included violent, sporadic outbursts before settling into its current state. The real intrigue lies in the nebula's chemical fingerprints. While its outer shell is rich in oxygen and nitrogen typical for planetary nebulas, its inner turbulence is laced with neon, an element usually forged deep in stellar cores. This mismatch implies the star didn't shed its layers evenly but convulsed, dredging up pockets of primordial material from its guts before finally exhaling its smoother outer shell. Imagine a volcano that first erupts chaotically, then finishes with a slow, steady flow of lava. The lemon slice's structure might capture both phases in a single celestial snapshot. What makes IC3568 truly exceptional, though, is its rarity. In a universe where most dying stars sculpt complex, asymmetrical farewells, this nebula's simplicity stands out. Some researchers speculate that what we're seeing is a fleeting moment of equilibrium, a brief window where turbulence within gets overshadowed by symmetry without. Given time, even this serene bubble might distort, its outer layers eroded by interstellar winds or reshaped by unseen forces. The lemon-sliced nebula forces us to confront a humbling truth. Sometimes the universe's quietest objects hide the loudest secrets. Its perfect sphere isn't proof of a peaceful death, it's a cosmic magic trick, a reminder that even the simplest structures can cloak galaxies' worth of chaos beneath their glow. The frosty Leo Nebula era's 09371 plus 1212 might sound like something from a cosmic dessert menu, but this celestial oddity serves up far more than just icy visuals. Lurking within its frigid embrace are organic molecules so complex, they're rewriting our understanding of stellar chemistry. While most dying stars sprinkle space with simple compounds like carbon monoxide or hydrogen cyanide, frosty Leo is a molecular factory, churning out elaborate carbon-based structures that resemble the building blocks of life itself. At first glance, the discovery seems paradoxical. Planetary nebulas are born from stars in their death, through environments scorched by ultraviolet radiation and buffeted by shock waves. Yet somehow, frosty Leo's outer layers have become a refuge for delicate organic molecules, including polycyclic aromatic hydrocarbons or PAH. These intricate carbon rings, often found in interstellar dust clouds, shouldn't survive the violent conditions of a star's final act. Picture trying to assemble a house of cards in the middle of a hurricane. That's the level of improbability we're dealing with here. So how does frosty Leo defy the odds? The answer lies in its unique anatomy. Unlike typical planetary nebulas, where ultraviolet radiation from the central star shreds complex molecules, frosty Leo's progenitor expelled its outer layers in an unusually dense, slow-moving shell. This created a protective cocoon of gas and dust, shielding the delicate organics from the star's harsh glare. Think of it as a cosmic freezer, cold enough to preserve fragile compounds, yet chemically active enough to foster their formation. The implications are staggering. If dying stars can forge complex organics in such hostile environments, the universe might be seeding galaxies with life's raw materials far more efficiently than we imagined. Frosty Leo's molecules aren't just curiosities. They're potential precursors to amino acids, the very stuff that makes up proteins. Some researchers speculate these compounds could hitch rides on comets or asteroids, eventually raining down on young planets like ancient cosmic care packages. But the real shocker, frosty Leo's organics aren't uniform. Observations reveal staggering chemical diversity, with molecules distributed in distinct zones like layers in an onion. Some regions are rich in acetylene, others in formaldehyde, each a snapshot of different temperatures and pressures within the nebula's expanding shell. This chemical patchwork suggests the star didn't die in one dramatic burst, but in stages, each ejection leaving behind a unique molecular fingerprint. The discovery forces us to reconsider stellar deaths as more than just destructive events. There are also cosmic kitchens where the violence of a star's demise becomes an unlikely chef, cooking up ingredients that might one day spark life elsewhere in the universe. And if frosty Leo's recipe is any indication, the menu is far more elaborate than we ever dared to dream. Among the countless planetary nebulas strewn across the cosmos, the Turtle Nebula NUC 6210 stands out not for flashy jets or violent outbursts, but for something far more puzzling: its glacial pace. While most nebulas expand at breakneck speeds, hurling material outward at hundreds of thousands of kilometers per hour, the Turtle lives up to its name, crawling along at a fraction of that velocity. Its leisurely expansion defies every expectation, leaving astronomers scrambling to figure out what cosmic breaks are slowing its spread. At the heart of this mystery lies a paradox. The nebula's central star is anything but sluggish. It's a white dwarf blazing at over 80,000 degrees Celsius, pumping out enough ultraviolet radiation to ionize the surrounding gas. Yet instead of racing outward, the nebula's outer edges inch forward at a mere 20 to 30 kilometers per second, slower than some comets' orbital speeds. It's like watching a rocket engine fire at full throttle while the spacecraft barely moves, a celestial conundrum that shouldn't exist, the leading theory. Magnetic fields acting like cosmic rains. Observations reveal the Turtle's structure isn't just slow. It's eerily ordered, with filaments and loops aligned in patterns that suggest an invisible magnetic scaffold. If confirmed, this would mean the dying star's magnetic field never fully dissipated as it collapsed. Instead, it might have intensified, wrapping around the ejected material like a net, channeling and restraining its expansion. Picture a handful of iron filings scattered around a magnet, their movements dictated by unseen forces. The Turtle's gas could be similarly enslaved, its outward rush stifled by magnetic lines we can't directly see. But there's a twist. Not all regions of the nebula obey this slowdown equally. High-resolution images show patches where gas appears to have broken free, forming faint streamers that stretch beyond the main shell. These rebellious tendrils hint at a tug-of-war between magnetic confinement and the star's radiation pressure, a battle where physics plays out in extreme slow motion. What makes the turtle truly exceptional is its rarity. Of the thousands of known planetary nebulas, only a handful exhibit this combo of a ferociously hot star paired with a lethargic nebula. That uniqueness makes it a laboratory for testing how magnetic fields influence stellar deaths, a process that might be more common than we realize, just usually invisible in faster expanding nebulas. And then there's the bigger question: is the turtle slow or just old? Some models suggest it might not be breaking at all, but instead represents a later stage of evolution where the nebula's initial momentum has nearly dissipated. If true, it could be a preview of our own sun's eventual fate, not a dramatic explosion, but a slow, magnetic fade into the cosmic night. Either way, this celestial tortoise challenges our assumptions, proving that sometimes the universe's quietest rebels are its most enlightening. The Water Lily Nebula, M192, blooms in the cosmic darkness like an interstellar garden, its delicate petals unfurling across light years of space. But this isn't just celestial artistry. Those intricate loops and swirls are the scars of a stellar tantrum, shaped by forces so violent they defy conventional models. While most planetary nebulas expand symmetrically, M192's flower-like structure suggests something far more chaotic at play, a precessing jet wobbling like a spinning top as it carves the nebula's signature petals into the void. Picture a garden sprinkler spinning erratically, its streams tracing spirals in the air. Now imagine that sprinkler is a dying star, and the water is superheated plasma screaming outward at 500,000 miles per hour. That's the scene astronomers suspect unfolded here. The central star's jet isn't firing steadily, it's lurching, its axis slowly circling due to gravitational tugs from an unseen companion or the star's own unstable rotation. Each wobble etches a new petal into the nebula's structure, creating layers of glowing gas that resemble the concentric rings of a water lily. What makes this nebula truly extraordinary is its rarity. Most jet-driven nebulas, like the Twin Jet or the Ant, display clean, bipolar outflows. M192's spiraling petals are a cosmic fingerprint, evidence that precession can sculpt nature's most elegant forms from stellar chaos. Hubble's sharp eye reveals even finer details, knots and braids along the petal edges, where shocks from the jet's erratic path superheated the gas into luminous filaments. It's as if the star's death throes were captured in stop motion, each violent tremor frozen in glowing ink. Compare this to other botanical nebulas and the contrasts are striking. The Tulip Nebula in Cygnus owes its shape to interstellar winds buffeting its gas, while the Rose Nebula's spirals stem from a binary star's gravitational dance. But the Water Lily's petals are purely the work of momentum, a dying star's final spins immortalized in plasma. Even its central engine remains enigmatic. Some models suggest the precessing jet arises from a disk of debris around the star, warped by magnetic fields. Others argue the star itself is tumbling, its poles tracing circles as it collapses. The real marvel, M192's petals aren't just pretty, they're clocks. By measuring their curvature, astronomers can backtrack the jet's precession rate, an astronomical detective trick revealing the star's spin history. Those graceful arcs encode millennia of stellar physics waiting to be decoded, and as telescopes peer deeper, they're finding more of these floral wonders, suggesting that what we once dismissed as cosmic oddities might be part of a hidden pattern, a reminder that even in death, stars can leave behind gardens of light. NGC 7027, better known as the Cotton Candy Nebula, looks nothing like its namesake sugary treat. Instead, it resembles an explosion frozen mid-burst, its wispy tendrils strewn chaotically across space. Unlike the crisp rings of the Saturn Nebula or the symmetrical wings of the Twin Jet, this cosmic cloud is a tangled mess, glowing with the frenetic energy of a star caught in the act of reinventing itself. The prevailing theory: we might be witnessing the aftermath of a rare thermal pulse, a violent resurgence of nuclear activity in a dying star that should have already faded into quiet oblivion. Thermal pulses are cosmic second winds, brief, violent revivals where a dying star reignites fusion in its outer layers, blasting fresh material into space like a phoenix refusing to burn out. For NGC 7027, this could explain its shredded appearance. Imagine a candle sputtering back to life just as it's about to flicker out, sending wax flying in all directions. That's the kind of turbulence astronomers suspect sculpted this nebula's frayed edges. The star at its center, now a white dwarf, might have surged back to life multiple times, each outburst layering new chaos onto the expanding wreckage. But here's where the debate ignites. Some researchers argue the cotton candy's fluffiness isn't from a thermal pulse at all, but from a brutal collision between stellar winds. The central star, they propose, didn't just die, it convulsed, ejecting material at wildly different speeds. Fast winds from its final death throes plowed into slower-moving debris from earlier outbursts, shredding the nebula into those eerie, filamentary wisps. It's like seeing the aftermath of a high-speed crash where faster cars rear-end slower traffic, leaving twisted metal in their wake. Adding to the mystery, NGC 7027 is unusually young. Most planetary nebulas take millennia to form, but this one might be less than 1,000 years old, a cosmic infant by stellar standards. Its youth could explain why it hasn't yet settled into a recognizable shape, its chaos preserved like a crime scene before the evidence scatters. Infrared observations reveal another twist. The nebula's core is laced with complex organic molecules, including hydrocarbons that typically get obliterated by a star's radiation. Their survival hints at sheltered pockets within the turmoil, like finding intact furniture in the rubble of a tornado. What makes the cotton candy truly bizarre is its asymmetry. Unlike the Helix's nested rings or the southern crab's hourglasses, this nebula has no discernible pattern. Its gases glow brightest in uneven patches, as if the star's death spasms were lopsided, perhaps due to a magnetic field gone haywire or an unseen companion star tugging at the ejector. Even its chemical composition is uneven, with nitrogen-rich regions bordering zones dominated by oxygen, a clue that the star's interior layers weren't shed evenly. Yet amid the disorder, there's a strange beauty. The same forces that tore this nebula apart also enriched it, seeding its filaments with the raw materials for future stars and planets. Its chaos isn't just destruction, it's recycling on a galactic scale. And for astronomers, that unpredictability is the real gift. The Cotton Candy Nebula refuses to fit neatly into models, challenging us to rethink how stars die when they're given one last turbulent encore. One thing's certain, this isn't just another pretty cloud. It's a cosmic storm frozen in time, a reminder that even in the vast, ordered cosmos, some stars go out kicking and screaming, leaving behind not serenity, but a masterpiece of glorious disarray. The Jewel Bug Nebula NGC 7027 unfolds through space like a shattered stained glass window, its fractured layers glowing in vivid blues, fiery oranges, and deep purples. But these aren't random splashes of color. Each hue is a cosmic fingerprint, marking where different elements forged in the star's violent death throws now fluoresce under the glare of its remaining core. Oxygen burns blue-green, hydrogen blushes red, and nitrogen stitches through the chaos in rich purples, a spectroscopic palette that reveals this isn't just one shell, but a series of nesting dolls, each layer a snapshot of the star's episodic unraveling. What makes the Jewel Bug extraordinary isn't just its beauty, it's the sheer violence encoded in those layers. Most stars shed their outer envelopes in a steady, if turbulent, wind. NGC 7027's progenitor, though, seems to have died in fits of rage, convulsing every few thousand years to blast fresh material into space. Imagine a volcano erupting, then sealing its crater, only to explode again moments later, each outburst freezing into a new shell. Here, the star's tantrums left behind concentric waves of gas, some surging outward at over 600,000 kilometers per hour, others oozing slower like cosmic molasses. The collisions between these layers created shock fronts that heated the gas to millions of degrees, igniting the nebula's eerie glow. Zoom in and the chaos deepens. Infrared observations reveal filaments of carbon-rich dust weaving through the shells, along with unexpected compounds like hydrogen cyanide and even formaldehyde molecules that shouldn't survive the ultraviolet onslaught from the central star. This chemical zoo suggests the star's death wasn't a linear process. Instead, it might have briefly reignited fusion in fits of thermal pulses, dredging up carbon and other heavy elements from its core and flinging them into space before collapsing for good. The result, a nebula that's not just expanding but practically boiling, its layers churning with ingredients for future planets or even life. The jewel bug's final act might be its most revealing. Unlike the symmetrical rings of the Helix or the crisp edges of the Saturn Nebula, this nebula's shells are wildly asymmetrical, some lobes jutting outward like shattered pottery shards. This lopsidedness hints at a hidden gravitational puppeteer, perhaps a binary companion whose tugs distorted the dying star's ejections, or a magnetic field so twisted it acted like a cosmic cookie cutter, shaping the outbursts into these jagged forms. Yet amid the violence, there's a strange elegance. Those colorful layers aren't just debris, they're a stellar autobiography written in light and gas. Each shell records a chapter in the star's death, the temperatures it reached, the elements it uncovered, the forces that tore it apart. And as telescopes peer deeper, they're finding more of these layered nebulas, suggesting that what we once called messy deaths might be the universe's way of recycling stars with brutal precision. The jewel bug doesn't just glow, it speaks, its chromatic whispers revealing how even in chaos, stars leave behind legacies as intricate as they are explosive. The Tulip Nebula Sharpless 101 blooms in the constellation Cygnus like a celestial flower, its delicate petals of ionized gas stretching over 30 light-years across the cosmos. At first glance, it's easy to mistake this radiant cloud for a planetary nebula, with its vibrant hues and intricate structure. But here's the twist: this cosmic tulip isn't the farewell kiss of a dying star. It's a sprawling stellar nursery, a vast region where new stars are being born, not a grave marker for one that's ended. The confusion between Sharpless 101 and planetary nebulas stems from their superficial similarities. Both glow with the same ethereal light, their gases energized by the radiation of nearby stars, but the differences beneath the surface couldn't be more dramatic. Planetary nebulas form when a single star sheds its outer layers in a final, luminous exhale. The tulip, on the other hand, owes its brilliance to the collective fury of massive young stars embedded within it, stellar infants so hot and energetic their ultraviolet radiation sets the surrounding hydrogen ablaze, painting the nebula in vivid reds and pinks. Zoom in and the distinctions grow sharper. Planetary nebulas like the cat's eye or helix often display intricate, symmetrical shells sculpted by the dying star's winds. The tulip's form, by contrast, is shaped by chaos stellar winds and radiation pressure carving its delicate curves into the interstellar medium. Some sections glow brighter where newborn stars cluster, while shadowy lanes of dust weave through its petals, hiding protostars still cocooned in their birth clouds. Yet the tulip's allure isn't just about its classification. This nebula holds a cosmic secret. It lies along the same line of sight as an even more distant and enigmatic object, Cygnus X1, one of the strongest known black hole candidates in our galaxy. While the two aren't physically connected, the alignment creates a breathtaking tableau, a radiant flower seemingly poised above the abyss. For astronomers, Sharpless 101 is a reminder that the universe loves to blur the lines between life and death. The same forces that sculpt planetary nebulas' radiation, stellar winds, and shock waves also shape these stellar nurseries, but with opposite outcomes. One marks an ending, the other a beginning, and in the tulip's case, the irony is poetic. A nebula often mistaken for a tomb is actually a cradle, its beauty a testament to the cycles of creation that play out across the cosmos. So the next time you gaze at this cosmic bloom, remember, it's not just a pretty illusion, it's a vibrant, living ecosystem where the seeds of future stars are sown in the glow of those already shining. A reminder that even in the vastness of space, the line between birth and death is often written in the same radiant script. Hidden within the twisted lobes of the Peanut Nebula MZ3 lies a cosmic secret that could rewrite the rules of stellar farewells. While most planetary nebulas owe their shapes to the death throes of single stars, MZ3's bizarre, pinched waist and elongated lobes scream of gravitational interference. The smoking gun, a suspected binary star system lurking at its heart, locked in a dance so intimate it's nearly impossible to spot. Detecting these stellar duos is like trying to find a flashlight in a blizzard. The primary star, now a white dwarf, blazes with enough ultraviolet light to drown out its potential companion. Add to that the nebula's own glow, a chaotic mix of ionized gas and dust, and you've got a cosmic needle in a haystack scenario. Yet astronomers persist because the stakes couldn't be higher. If confirmed, this hidden partnership would explain the Peanut's signature shape. Two stars orchestrating their ejections like dueling conductors, their gravitational tugs squeezing the outflow into those distinctive lobes. The evidence is tantalizing but indirect. Spectroscopic studies reveal subtle wobbles in the nebula's core, hints that something unseen is perturbing the white dwarf's position. Infrared observations peek through the dust, uncovering an excess of heat that could betray a cooler companion star. Even the nebula's chemistry tells a story. Odd nitrogen-rich patches suggest material was dredged up from one star's depths and flung into the mix by gravitational chaos. But the real challenge lies in the timing. Binary stars in planetary nebulas often have orbital periods measured in days, making their movements dizzyingly fast by cosmic standards. Catching them mid-pirouette requires observations spaced hours apart, a logistical hurdle when telescope time is precious. Some researchers have turned to AI, training algorithms to spot the telltale flickers of a hidden partner in decades-old data. Others are banking on luck, waiting for the rare moment when the companion might eclipse the white dwarf, casting a detectable shadow. What makes MZ3's potential duo so fascinating isn't just their elusiveness, it's their legacy. If confirmed, they'd join a growing list of binary-shaped nebulas, proving that many of the cosmos' most breathtaking structures aren't solo acts. They're collaborations forged in the gravitational push and pull of stars that refuse to die alone. And in the Peanut's case, that partnership didn't just shape its goodbye, it turned it into one of the universe's most striking cosmic sculptures. The Mimosa Nebula, Hen 2437, drifts through space like a whisper of violet smoke, its delicate tendrils so faint they barely register on telescopes. Named for its resemblance to the fine petals of a mimosa flower, this celestial anomaly isn't just beautiful, it's vanishing before our eyes. Unlike the helix or the cat's eye, which glow brightly for millennia, Hen 2437 is dissipating at a breakneck pace, its structure unraveling so quickly that astronomers can almost watch it fade in real time. What makes this nebula's fleeting existence so puzzling? The answer lies in its ghostly composition. While most planetary nebulas shine brightly thanks to dense gas ionized by their central stars, the Mimosa's filaments are wispy and diffuse, more like cobwebs than clouds. Without enough material to efficiently absorb and re-emit starlight, the nebula's glow is vanishing as fast as its gases disperse into the void. Imagine blowing soap bubbles on a windy day. Their fragile shells vanish almost instantly, leaving no trace behind. The Mimosa Nebula is the cosmic equivalent, its structure too delicate to withstand even the gentle pressure of interstellar space. Yet there's a deeper mystery here. Nebulas like the Medusa fade over tens of thousands of years, but HEN 2437's timeline is compressed into mere millennia, a blink in cosmic terms. The culprit might be its progenitor star, a white dwarf that cooled unusually fast, starving the nebula of the ultraviolet radiation needed to keep it luminous. Most central stars remain scorching hot for eons, but this one seems to have shut off like a switch, leaving its nebula to wither in the dark. But the real shocker comes from the nebula's motion. Observations reveal it's plowing through a denser-than-average patch of interstellar medium, like a ship battling headwinds. The friction from this collision is stripping away its tenuous gases at an accelerated rate, shredding the mimosa's petals into indistinguishable mist. It's a reminder that nebulas don't exist in isolation. Their fates are shaped by the invisible oceans of gas and dust they traverse. And then there's the tantalizing question of how many others like it we've missed. If HEN 2437 is any indication, the cosmos might be littered with evanescent nebulas that flared into view and vanished before our telescopes could catch them. The Mimosa's fleeting glow challenges our assumptions about stellar deaths, proving that some stars don't leave behind monuments, just vanishing acts as ephemeral as the scent of a flower on the solar wind. Hovering in the constellation Orion like a phantom mid-flight, the cosmic bat nebula NGC 1788 unfolds its shadowy wings across 20 light-years of space. This eerie silhouette isn't just a trick of perspective. It's a cosmic interplay of light and darkness so precise, it looks as if the universe itself took a paintbrush to the void. Unlike the radiant glow of planetary nebulas, the bat's drama unfolds in negative space, where dense lanes of dust blot out starlight to carve its unmistakable shape. The secret to this celestial chiaroscuro lies in the nebula's dual nature. Its wings are colossal ribbons of interstellar dust, so thick they absorb nearly all visible light passing through them. But these aren't static curtains, they're dynamic structures, buffeted by stellar winds from young, massive stars hidden within the cloud. These invisible sculptors bombard the dust with radiation, eroding some regions while compressing others into even denser knots. The result, a natural stencil where gaps in the dust allow background starlight to seep through, tracing the bat's JAGGED Chinese letter with ethereal highlights. Zoom in and the illusion grows richer. The darkest patches aren't uniform, they're frothy with microscopic carbon and silicate grains, each 1,000,000 times smaller than a grain of sand. These tiny particles scatter blue light but devour red wavelengths, giving the bat's wings their rusty, muted tones, a phenomenon eerily similar to Earth's sunsets, where dust in our atmosphere reddens the fading light. Yet here, the process unfolds across light years, with entire star clusters playing the role of the sun. But the real magic happens at the edges. Where the dust thins, it glows faintly in infrared, a thermal fingerprint of hidden energy. Embedded stars, too young to have blown away their natal cocoons, heat the surrounding dust like embers in a cosmic campfire. Their warmth radiates at wavelengths invisible to our eyes but palpable to telescopes like Hubble and Spitzer, revealing the bat's true complexity. This isn't just a shadow puppet, it's a stellar nursery veiled in darkness where new stars ignite behind curtains of their own making. What makes NGC 1788 truly uncanny is its fleeting nature. Unlike the enduring glow of planetary nebulas, the bat's silhouette is temporary. Those dust lanes are dissipating atom by atom as the very stars they birth dissolve them with their radiation. In a few million years, a blink in cosmic time, this haunting figure will unravel, its dust recycled into new generations of stars and planets. For now, though, it soars through Orion as a reminder. Sometimes the universe's most striking artistry isn't in the light it shines, but the shadows it casts. From the Butterfly Nebula's supersonic wings to the Calabash Nebula's explosive encore, we've uncovered 30 cosmic wonders that shatter every expectation of how stars die. These aren't just pretty space clouds, they're celestial crime scenes, each revealing clues about the violent, beautiful chaos of stellar farewells. Take the Medusa Nebula, fading faster than a whisper, or the Stingray Nebula, transforming before astronomers' eyes, proof that the universe writes its rules in disappearing ink. What ties these enigmas together? A single humbling truth: stars refuse to die quietly. They convulse in magnetic tantrums, sculpted by unseen companions, or even resurrect themselves in thermal pulses. The Lemon Slice's serene shell hides a stormy heart, while the Necklace Nebula's diamonds are relics of stellar cannibalism. Every discovery peels back another layer of cosmic mystery, forcing us to rewrite the playbook on stellar evolution. These nebulas are more than final acts, they're recycling plants on a galactic scale. The frosty Leo's organic molecules and the jewel bug's layered chemistry prove that death seeds new life, scattering the building blocks of future worlds. Even their imperfections teach us. The little dumbbell's lopsided glow and the peanut's hidden binaries reveal how chaos births beauty in the cosmos. So as we close this journey, remember, each of these 30 strangest nebulas started as someone's normal discovery until closer inspection revealed their secrets. That's the real lesson. The universe always has another surprise waiting. Now it's your turn. Which of these cosmic rebels left you awestruck? Was it the Saturn Nebula's perfect rings, the ant's eerie mimicry, or the bat's shadowy wings? Drop your pick in the comments and keep looking up. The next great mystery might already be glowing in the